Everyone, we are on to our last integration technique, which is called integration by partial fractions. Now, we covered partial fractions in pre-cal, but in case you forgot how to do them, there's a little bit of instructions right here. But I'm going to go ahead and proceed as if you remember exactly what you're doing. Okay, so the idea behind partial fractions is to kind of split our denominator. So in this case, I have 4x plus 41 divided by, now I'm going to factor the bottom here into x plus 5 and x minus 2. Okay, and what I want to do is split this into something over x plus 5 plus something over x minus 2. Okay, I want to split this up because as it is right now, I'm not going to have a whole lot of luck integrating this, but if I can split this into two linear functions, it's very easy to integrate. Both of these would just be natural log. Right, but I just have to figure out what a and b are. So the way I do that is I set this up, and then I multiply both sides by my denominator. Okay, so I'm going to multiply both sides by x plus 5 times x minus 2, and that will cancel out my denominator here. And that will cancel out one of each of these. So I'll have a times x minus 2 plus b times x plus 5. Okay, so I just multiplied both sides by the denominator here on the left. Okay, and then from here, I'm just going to plug in numbers for x, honestly. So I'm going to let x equal 2. The reason why I want to do that is because that will eliminate my a variable and just leave me with b. So if I plug 2 in for x, I get 49 equals 7b. Okay, that means that b equals 7. Right? And if I let x equal negative 5, that means that 21 equals negative 7a, and so a equals negative 3. Right, so that means I can rewrite this as negative 3 over x plus 5 plus 7 over x minus 2. Okay, so this whole situation here is equivalent to this, and that's what partial fractions does. So now if I rewrite my integral using my decomposition, it'll be much easier to integrate. Okay, now you could split this into two integrals if you want. You don't have to, okay, but the end product is pretty straightforward. It's just natural log. Right, and that's it. That is my partial fraction decomposition integral. All right, let's move on to another example. All right, so slightly different process here. So again, I'm just going to set up my equations. Right, but the way that I set these up this time is I have a over x, and then because my term here is squared, the multiplicity is 2 there, I'm going to kind of split that up into x plus 1 and x plus 1 squared. Okay, so if I have a whole term or a group that is to some exponent, then you kind of decompose that kind of 1 power at a time until you get what you want. Okay, and on top, you just keep going with constants a, b, and c. Okay, once again, I'm going to multiply both sides by my denominator. And so I just have 5x squared plus 20x plus 6 on the left side. On the right side, I end up with x plus 1 squared times a plus x times x plus 1 times b plus just x times c. All right, now what I'm going to do is distribute this out, do my binomial distribution, and same thing here, I'm going to distribute this. All right, and then I'm going to distribute my a and my b values as well. So I have ax squared plus a times 2x plus a plus b times x squared plus b times x, and then plus c times x. All right, now what I want to do at this point is group my like terms together. Okay, so I see that I have ax squared and I have bx squared. So these are like terms because they both have an x squared. Remember, a and b are just constants. Okay, and then I'm going to group my linears together. So I see I have 2ax and bx, and then last are my I have cx right there as well. And then last are my constants, which is just a. So a is my constant here. Okay, next step, I'm going to factor out. Right, so both these have an x squared in common. I can factor x squared out. Okay, all of these have an x in common. So I'm going to factor out an x, and then a is my constant. And remember, all of this is equivalent to 5x squared plus 20x plus 6. Right, so now what I can do is equate these. Right, so I have my term here and my term here. X squared and x squared are equal. That means that 5 has to be equal to a plus b. Right, so now I can set up a system of equations. So I know that 5 is equal to a plus b. Okay, if I look at my just linears here, I see that 20 has to be equal to 2a plus b plus c. So I'm just setting my coefficients equal to each other. Right, and then last, I see that my constant has to be equal to my constant. So 6 has to be equal to a, which is real nice. That tells us one of our constants right away. Okay, so I know that a equals 6. That means right here, because a plus b equals 5, that means that b has to equal -1. And that means that from here, right here, so 20 equals 12 minus 1 plus c, that means that c has to equal 9. So I have kind of my 3 constants solved for right here. So I'm just going to plug them into here. So that means that I have 6 over x plus -1 over x plus 1 plus 9 over x plus 1 squared. Okay, so this is my partial fraction decomposition, and so I'm going to now rewrite my integral using my partial fraction decomposition. Okay, now I'm going to clear this just for space. So now I have the integral of 6 over x plus -1 over x plus 1 plus 9 over x plus 1 squared dx. Right, this is pretty straightforward to integrate. Here I just have 6 natural log of x minus natural log of x plus 1. Right, and then this isn't going to be natural log because it's x plus 1 squared. So this is going to be -9 x plus 1 to the -1 power plus c. Right, and if you have trouble doing this by just in your head, then you could do a u sub for this one. Okay, so this is my answer. Let's move on. Last problem. Okay, so here I have a linear on the bottom and a quadratic, and this involves just a step extra. Right, so this is going to be very similar to the previous problem where we're going to set up a system of equations. So when I'm setting this up, I get a over x plus 1, and if you have a quadratic in the denominator here, then on top you're going to want a linear. So I set this up as bx plus c. Okay, so I have a quadratic on bottom, on top I have a linear in mx plus b form, but instead of using m and b, I'm using b and c as my variables just to make things easy. Okay, again, I'm going to multiply both sides by my denominator on my left side. So I get 7x squared plus 5x plus 23 equals x squared plus 4a plus x plus 1 times bx plus c. All right, now I'm going to distribute everything. So I have ax squared plus 4a plus bx squared plus bx plus cx plus c. Right, and again, I'm going to get combined like terms. I'm going to group. So I have ax squared and bx squared. Then I have bx and cx. And then I have 4a and c. Right, so those are my constants. So here are my quadratics. Here are my linears. Here are my constants. Right, and again, I'm going to factor out now. So a plus b x squared. B plus c x. And then just 4a plus c is my constants. And again, this is all equivalent to 7x squared plus 5x plus 23. Okay, so I can set up my system. So I know a plus b has to be equal to 7. I know b plus c has to be equal to 5. And 4a plus c has to be equal to 23. Okay, so we can solve this, and it's not too bad. I'm gonna use this bottom equation here, and so I can solve for b in terms of a, Then here I can solve for c in terms of b and just substitute everything into this last equation. You don't have to do it this way, but I'm choosing to. So 4a plus c is the same thing as 5 minus b, but b is the same thing as 7 minus a. Okay, so I just substituted and I substituted, and I got a, nothing but a in my equation. Okay, now I'm going to solve for a, so minus and negative becomes plus, so I have 5a, 5 minus 7 is negative 2, equals 23. Add 2 to both sides, and then divide. Alright, so I get a to be 5, if I plug that into here, I get b to be 2, if I plug this into here, I get c to be 3. Alright, so my partial fraction decomposition finally looks like this. 5 over x plus 1 plus 2x plus 3 over x squared plus 4. Okay, so now I can integrate this. It's going to be a bit extra, but that's fine. Right, so in my integral, I have 5 over x plus 1 plus 2x plus 3 over x squared plus 4 with respect to x. Now what I'm going to do is actually split this fraction up. So 5 over x plus 1, 2x over x squared plus 4, and then 3 over x squared plus 4. Right? The reason why I did that is because I can do this easily using a u-sub, and this is actually my arctangent. So if you're having trouble seeing that, right here we could do a u-sub, so you would let u equal x squared plus 4, du is 2x dx, so this is going to be natural log. Right here, I guess my x is x, or my u is x, and my a is 2, right? And so I see that this is arctangent. All right, so I can jump straight to my answer. So the integral of 5 over x plus 1 is going to be 5 natural log x plus 1. Okay, right here I see my derivative is on top and my original function is on bottom, so this is just straight up natural log x squared plus 4. And then right here I have a 3, but remember it's actually 1 over a, so it's going to be 3 over a, which is 2, arctangent of x over 2, and then plus c at the very end, right? And this is my integral using partial fraction decomposition. Okay, so that's it for these notes. See y'all later.